The Jovian planets. Like the other planets, most of what we know about the Jovians come from spacecraft that we have sent out to visit. The first spacecraft to visit Jovian planets was Pioneer, and this was in the 1970s. Pioneer flew past both Jupiter and Saturn. And we got our first nice up-close images of these worlds. The next spacecraft to visit were two, Voyager 1 and 2. Voyager 1 also flew past Jupiter and Saturn. Voyager 2 is the only spacecraft to have visited all of them. So not only did it visit Jupiter and Saturn, but also Uranus and Neptune. These missions were launched in the 1970s. The Neptune flyby was in 1989. So you can see the kind of time scale to visit all of these planets. Both Voyager 1 and 2 are actually still sending back information. They're now traveling out away from our solar system, but they're now measuring our sun's magnetic field. And there is a possibility that Voyager 1 has reached the boundary of our sun's magnetic field, which is kind of considered the beginning of interstellar space. After Voyager, it wasn't until the 1990s that we put Galileo in orbit around Jupiter. And this gave us wonderful images not only of Jupiter but of its moons. It sent a little probe that plunged into the clouds of Jupiter, and just realized I misspelled Galileo. It gave us some measurements about the clouds of Jupiter. Now, it got crushed long before it went very deep because atmospheric pressures on Jupiter are insanely high. And still going is Cassini, which is orbiting Saturn and has been giving us wonderful images of Saturn and its rings and its moons, making all sorts of measurements. And associated with Cassini was a probe called Huygens, which landed on one of Saturn's moons, Titan. And when we talk about the moons of the Jovian planets, we'll learn more about that. When we look at the Jovian planets, we find that we really are dealing with two main groups. Jupiter and Saturn we lump together, and these two are kind of the gas giants because they have interiors that are primarily gas. Uranus and Neptune we lump together. These are sometimes called the ice giants because they have a large layer of ice in their interior. So a lot of characteristics we'll see Jupiter and Saturn are very similar to each other, and then Uranus and Neptune very similar to each other. Of course, all the Jovian planets are large. Here we see how big the Jovians are compared to the terrestrial planets down here. And then, of course, poor little Pluto. And of all of them, of course, Jupiter is the biggest. In fact, if you took all of the other planets, moons, asteroids, everything else in the solar system, and combined it together, Jupiter would still have more mass than all of that combined. So in terms of hierarchy in our solar system, the Sun comes first. It's much, much bigger than Jupiter. Jupiter is the next biggest influence in our solar system. The density of the planets, of course, is related to their composition. You're looking at mostly hydrogen and helium, which are low-density materials. And so the Jovian planets are going to have very, very low densities. Saturn has the lowest density of them all. In fact, it has a density less than the density of water, which means that Saturn can float in water. And that's a very bizarre image because it is gaseous, but with such a low density, if somehow you had a body of water large enough, it would float in that water. Rotation rates of the Jovians are kind of surprising given their size. When we look at rotation rates, Uranus and Neptune are both around 17 hours. Jupiter and Saturn are both around 10 hours. And you think about, Earth, much, much smaller than all of these, and yet it takes us 24 hours to rotate. So we've got this humongous object, gaseous, rotating really fast. That's going to have an effect on its shape. And Jupiter and Saturn in particular are flattened because of this fast rotation. And it's not super obvious in this picture of Jupiter, but it is in fact a little bit fatter along the equator and a little bit flattened pole to pole. And Saturn even more so because of its low density. Uranus and Neptune not nearly as flattened as Jupiter and Saturn. The tilts of the Jovians are kind of all over the place. Jupiter, it has almost no tilt to its axis. Saturn and Neptune are both kind of similar to Earth. They're both around 20-degree tilts. The picture here is showing Uranus. Uranus has the most unusual tilt because it's about a 90-degree tilt. So as Uranus goes around the Sun, if this is the Sun and this is Uranus with its axis on its side, so it's rotating that way and then orbiting this way. So if this is, say, the North Pole and the South Pole, summer in the southern hemisphere here is going to be continuous sunlight. Winter in the northern hemisphere would be continuous darkness. And then half an orbit later, it's going to be reversed. The northern hemisphere is going to be in continuous sunlight, and the southern hemisphere is going to be in continuous darkness. So this gives Uranus very extreme seasons. The time it takes Uranus to go around the Sun is roughly 84 years, so each season is about 21 years each. So you've got 21 years of continuous sunlight. When you're over here, you would actually have 21 years of a day-night cycle, 21 years of continuous darkness, and then back to 21 years of a day-night cycle. So very, very unpleasant weather conditions, seasonal conditions on Uranus because of the extreme tilt. As we saw before, the composition of the Jovians is primarily hydrogen and helium, with this little bit of other stuff, rock, water, ammonia, methane, and a little bit of everything else kind of mixed in. But this is where the name gas giants comes from, because they are big and they're composed of gases. But when we look at the interiors, we see that that is kind of subdivided a little bit. At the center of all four planets, you have a core that is composed of rock and metal. So that's going to be this, thing in the middle here. Now this picture is not to scale. It's showing Uranus and Neptune bigger than Jupiter and Saturn. But it was just to get everything all one size on here. Now the cores are underneath basically these humongous atmospheres. So the pressures on the core are insane. It's about 10 million atmospheres of pressure on the core. So, we were concerned by the 90 atmospheres of pressure on Venus. This is beyond survivable. And that's why the little probe that was sent into Jupiter's atmosphere, on this scale, it barely went in at all before it started to get crushed. Outside of the core is a layer of ice, and in particular ammonia and methane ice. Now, ice in astronomy basically means anything that's a solid that we don't normally have as a solid here on Earth. So it's not shown in the Jupiter and Saturn cutaways, but it would be just outside of the core here would be the layer of ice. And it is this layer in Uranus and Neptune is the ammonia and methane ice layer. Now the next layer is only found in Jupiter and Saturn, and that is a layer of metallic hydrogen. Metallic hydrogen here is this large layer there. That is hydrogen under a lot of pressure. And what that pressure does is it actually separates electrons and protons in the atoms. So you've got free electrons and free protons swimming around. And because that will conduct electricity, chemists call that metallic. So that's why it's called metallic hydrogen. But the key is you need pressure. And Uranus and Neptune are smaller. They don't generate as much pressure, so they do not have a metallic hydrogen layer. The last layer that they all have is molecular hydrogen. This is essentially gaseous hydrogen. So in our cutaways, the yellow here in Jupiter and Saturn, or the dark blue here on Uranus and Neptune. And so the outermost layer, gaseous, then you get this transition for the big planets to this liquid metallic hydrogen layer. Then you've got the layer of ice, and then in the center you've got the core of rock and metal. When we look at the Jovians, though, what we're seeing are the clouds. And again, we lump Jupiter and Saturn together, and then Uranus and Neptune together. The clouds that we see on Jupiter and Saturn are primarily ammonia ice crystals. And cloud top temperatures are about negative 200 degrees Fahrenheit. And that's true for both Jupiter and Saturn. At distances from the Sun that we're dealing with, their temperature is dominated more by the heat from their interior than it is by the heat from the Sun. So in both cases, the cloud top temperature has more to do with the heat that's coming from the center and working its way out than it does the heat from the Sun. Notice that both Jupiter and Saturn, their clouds have this kind of yellow, orange type color, and that is the ammonia ice. Neptune and Uranus, you're looking at methane ice crystals for the clouds. And their cloud top temperatures are about negative 280 degrees Fahrenheit. And obviously they both have this lovely blue color, and that is due to the methane. Since we are dealing with planets that are essentially giant atmospheres, there's certainly going to be wind and weather phenomena taking place. One of the things we see on especially Jupiter and Saturn is that the fast rotation produces bands. So we see on Jupiter and to a lesser degree on Saturn, though we see that as well, we see this kind of alternating dark and light regions in the weather patterns. Those are actually alternating high and low pressure systems. The winds do go in opposite directions, as I indicated with the arrow. And so these are a result of that very fast rotation. The weather just becomes confined into these bands. Now on Jupiter, we also have a very noticeable feature, and that is this big round thing here. And that is, of course, the Great Red Spot. This is a storm. It has been around for longer than we know, because telescopes have been able to see it for a few hundred years, about 300-400 years, but we don't know when it actually first appeared. It is essentially like a hurricane. It circulates around, and it has changed over the years. It used to be about 5 times the size of the Earth. Now it's about a little under 3 times the size of the Earth. The color has changed. It used to be much more noticeably red. Now it's more of a brownish orange color. So we don't know how long it will last, if it is a permanent feature or not, but it certainly has been there for centuries. Now over here on Neptune, when Voyager 2 flew past Neptune in 1989, it saw this dark feature. And astronomers suck at naming things, so they called this the Great Dark Spot. Should over here label that this is Jupiter. So the Great Dark Spot was a storm, also large, and astronomers originally thought that it would be something like the Great Red Spot, some kind of permanent feature. That turned out not to be the case. It was the Hubble Space Telescope, about 10 years later, it was gone. So, obviously large storms do disappear. We don't know the mechanisms well enough to understand what generates these storms, why some of them do last for hundreds of years, and why some of them disappear. It's one of the things that we're still trying to figure out about the Jovian planets.